Hello, welcome to Notes 1E about matter in the periodic table. So you have two quick reviews here, mostly because there are things that I want to make sure we review, and I wanted to break it up into two different sections. So you're going to make sure that you use your word bank here to answer each. So this word bank goes with this section, and this word bank goes with this section. So pause, take a moment to fill that in as best you can, and then unpause it to get the answers. So the chart that shows all of the different ingredients of the universe is called the periodic table of elements. However, scientists do not call these things ingredients. They call them the elements. If you took a pure substance, something made of only one element, and kept cutting it smaller and smaller, eventually you would wind up with just one atom of that element. All right, now, notes 1D. This is the review of that one. So the parts of an atom are the proton, the neutron, and the electron. All right, before we answer it, let's review real quick. Here we go. The sillier it is, the better you remember it. Protons have a positive charge. Neutrons are neutral. And electrons are so negative. Right? Okay, so proton has a positive charge. Neutron has a neutral charge, and the electron has a negative charge. The protons and the neutrons are in the nucleus, and the electrons are in the cloud. Protons, neutrons, and electrons are called subatomic particles. All right, check yours. Moving on. All right, so today we're talking about the periodic table. So we've been talking about the periodic table with all the different ingredients. So if you were in class, I would ask someone to venture a guess as to how many elements we have been able to identify, naturally or unnaturally so far. And if you look at the periodic table, you can tell, like, what's the biggest number there? 118. So the answer is about 118. Now, here's the thing that you've got to understand about these ones that are in these higher numbers. They're not real. We assume that these elements can be made in a supernova, in a giant explosion of a star, but they don't last very long. They're very unstable. They are radioactive. They fall apart in 2 seconds. So they decay very quickly. So we assume that these exist because we've been able to make them in labs in certain, it's called a collider. And you literally like slam two atoms into each other and force them to make another larger atom. But it decays in moments. Sometimes it only lasts long enough to say, oh, and then it's gone. But those have been named. This row here, unfortunately, is not. They have names now. They were like ununcunctium and ununseptium and things like that because it was just Latin for 117, 118. But they now have been named. They all now have real names. They're not named on this one either, but you can't see it. But way back there, the one that's on the wall in the classroom, that one has the correct names on it. And if you look it up on the internet, you'll find all the new names. But for example, 118 is oganesson. Yeah. Anyway, I think 117 is flerovium. I don't know. But yeah, they do have names. Now, so how many are there then? About 92 are naturally occurring. So everything from 1 to 92 is naturally occurring. It can be found in nature. It can be found if you dig in the dirt. It can be found in the air, in the water, or whatever. It's a naturally occurring element. Now, there may not be very much of it. There's some of these elements that are lower than 92 that are very rare. Then there are also some that are radioactive. But all of the ones above 92 are man-made, not naturally found on Earth, and are highly radioactive. They're also super, super heavy. Okay, like the masses of these are insane as compared to other smaller atoms. So everything from 92 plus, well, we should say 93. 93 and up, because 92 is naturally occurring. Uranium, number 92, is naturally occurring. but everything after that is not. So 93 and up they're fake. What do I mean by that? They have to be man-made. We assume that they do occur naturally, but those processes don't happen on Earth. They are highly unstable. They are radioactive. They decay very quickly. And they are super heavy. And that should be one word, but I didn't quite have room. Super heavy just means they're very massive. So we also talked about the fact that the number of protons in the nucleus is what determines what kind of atom it's going to be. So if I say I have 6 atoms that I know are 6 protons that I know is carbon. If I say 26 protons that I know it's iron, can't be anything else. All right. So I hope that you can either use these notes. You can just scroll back down to the periodic table that's there and use that image. You can go to ptable.com. I highly recommend it. ptable.com. It's a very cool website. My T has an extra little leg on it. It's got very, very cool stuff going on. You can learn all sorts of things that you didn't really want to know, but you might find interesting on ptable.com. And you can use that to do this. So if you want to pull up ptable.com, and that way you can answer these questions. So what I want you to do is take a look at the number above each symbol. So I've got a periodic table here that I can bring in really closely. And we'll look at, what can we see here? We'll look at calcium. Can you see calcium? Where's calcium? There it is. There's calcium. Everything's backwards. All right, so if we're looking at calcium here, you can see that it has a bold number that is a whole number at the top. And then there's a decimal number that's not bold down at the bottom. The atomic number, this bold number, whole number up here at the top, that's the number that tells you the number of protons in the nucleus of the atom. So all calcium atoms have 20 protons. And you know that that's the atomic number because it's the number that's not a decimal. It's the whole number. So this atomic number, this whole number, tells you the number of protons in the nucleus of an atom. Now, it also can tell you the number of electrons. In a neutrally electrically balanced atom, if it has 11 positive charges, it's going to have 11 negative charges for it to be a neutral atom. So 11 protons, 11 neutrons. Listen to me. Electrons, 11 protons, 11 electrons. Don't listen to the neutron part. That one's different. We'll talk about that later. But the number of protons and the number of electrons are the same in an electrically stable atom. Now, there are such things called ions, which we will talk about in the next unit. Ions are different. Ions are going to have one number for the number of protons and then another number for the electrons. So that's why we don't always say period, it's the same number. But in an electrically neutral atom, there are the same number of protons and electrons. But we're going to stick with protons right now because that's the one that always stays the same. So if we look at our atomic number for each of these elements, what is the atomic number? What are the protons for each of these? So I want you to go to ptable.com, scroll up and use the periodic table that's above it on the notes if you can see it. I'm going to try to show you here. I tried using this, but I don't think this is going to be clear enough. So we're going to give this a shot. All right, so we're going to start with oxygen. Oxygen right there. So what is oxygen's atomic number? Right, 8. Okay, and then helium is right here. And that one's 2. And carbon, we already looked at carbon a little bit. Carbon's right there. Carbon has an atomic number of 6. And then radium is over here. Can you see that one? Radium. So radium's atomic number is 88. Back over to this side again for xenon, right there, xenon, and that's 54. And then we're back over here again for potassium. Okay, there, potassium is 19. So what would happen to a chlorine atom if it lost a proton? So first we got to find chlorine. So chlorine is a halogen, so it's over here on this side, Cl right there, and you can see it has 17 protons. So we know that the number of protons are what makes it chlorine. So if something happened where it started to decay and it lost a proton, what's going to happen? Well, it's not going to be chlorine anymore. It's going to now be sulfur because it's gone down one. It's lost a proton. So it would be sulfur. Why is it going to be sulfur? Because sulfur has 16 protons. All right, what about a hydrogen atom? What if it gained a proton? So hydrogen has 1 proton. So if it gained a proton, it's now going to have 2 protons. It's now going to be helium. Why is it going to be helium? Because helium has 2 protons. Okay, so we talked about protons being positive, electrons being negative, and in an electrically neutral atom, you have the same number of protons and electrons. So we got protons with our positive charge, we have electrons with our negative charge, and in a neutral atom, we're going to have the same number. So really quickly, just want to draw something to illustrate that. So let's look at beryllium. All right, so beryllium has 4 protons in the nucleus. And then it has an atomic number of 9, so that means it has 5 neutrons. And don't worry about, like, where did she get that from? You'll find out in a minute. We'll talk about it in just a second. I haven't been able to change the color on this. Oh, I can do it with this though. Okay, so, and then we'll do 1, 2, 3, 4 electrons in the cloud. And what I want us to pay attention to is the fact that there is 1 positively charged proton for every 1 negatively charged electron. All right. Protons and neutrons each have a mass of 1 AMU. AMU stands for atomic mass unit, and it's small. It's really, really small. So the electron mass is so small, we can ignore it. Now, if we were in class, I would be like, hold up, hold up, hold up, hold up. You know, how stupidly wicked small is a proton and a neutron? And someone would, be able to explain it to me some kind of way. And then I would say to you, okay, well then how stupidly, abnormally, crazy, nonsensically small must an electron be to just be ignored? If protons and neutrons, with them being so very small that, like, even if you blew up the size of an atom to the size of a football stadium, the nucleus would still only be like the size of a marble inside of it. That's how small they are, and yet they get a weight. And electrons are so small they don't. Yeah, I mean, whew. Okay. So when the protons and the neutrons are in the nucleus, they both have that weight of 1 AMU. So the atomic mass isn't just the number of protons. The atomic mass is the number of protons plus the number of neutrons. So when you're looking at a periodic table, that number is going to be the decimal number. So we looked, I think, at oxygen. I don't know. Let's look at oxygen. So when we're looking at oxygen, oxygen has an atomic. Well, no, I want one with an interesting decimal. Let's look at neon. Okay, so neon's atomic number is 20.18. So we know that that's the atomic number because it's the number on the bottom and it's the decimal number. Now, wait a second. How in the world can we have a decimal number? I mean, can we have partial protons and partial neutrons? Is it possible to have like a neutron and a half in this atom? No. Kind of like the national average for the number of children is like 2.4 kids. You can't have 0.4 kids. But when you average together, this family has 3, this family has 2, this family has 5, this family has none, this family has 1. When you average it all together, it comes out to 2.4. Well, of course, no one has 0.4 of a child. But averages give you decimals of whole numbers. So that's where the atomic mass comes from. It's an average. See, there are these things called isotopes. So for example, I could have 5 different carbon atoms, and each one of them could have a different number of neutrons. They would all be isotopes of carbon. So we'd have the one carbon atom that had 6 protons and 6 neutrons and was the average normal carbon atom. But then there's a couple of other isotopes. There might be a carbon atom that has 6 protons and 5 neutrons, and then 6 protons and 4 neutrons, and then another one that has 6 and 7 neutrons, and then another one that has 6 protons and 8 neutrons. So all of those are going to have different weights because that extra or lacking neutron adds or takes away weight. So you average together the masses of all of the isotopes of that atom, and that's where that average number comes from, that atomic mass number, the decimal number down at the bottom. So the average atomic mass number of any atom is the number, decimal figure, and I want you to, again, go to p-table, scroll up, whatever, and we're going to see if we can find the atomic mass for each of these. So first one on the list is oxygen. So there's oxygen. If you look down underneath, 16. So 16 is the mass for oxygen. Then helium is right up here, and helium is 4. Carbon right here. Carbon is 12.01. Sometimes it's 12.011111. It depends on what table you're looking at. Radium is over here. Radium is 226.03. 226 and 300ths. Xenon is also over here. Oh, nope, it's over here. My bad. That's what I get for looking at it upside down. Xenon, 131.29. Potassium, back over here. And that's 39.10. So the simple way to calculate the atomic mass of any atom is to add up the protons and the neutrons and the nucleus. Why don't we add the electrons? Right, because they're so small we ignore them. All right, every element in the periodic table of elements has a code to represent its name. The code for each is either 1 or 2 letters and is called the chemical symbol for that element. So you already know hydrogen, that's the chemical symbol for hydrogen. You already know nitrogen and oxygen. Most of you know carbon and sulfur. So CHONS, I did that backwards. CHONS is the way to remember what are the most common elements in living things: carbon, hydrogen, oxygen, nitrogen, and sulfur. All right. So we're going to look at, I want you to realize that periodic tables can look all kinds of different ways, and I want you to be able to identify what is where. Where's the atomic number? Where's the symbol? Where is the atomic mass? And then I also need you to realize that that is not always there. The name is not always there. If you look at the one that's on the wall here in class, it is the names are not on there. When you take the SOL, the names are probably not going to be on there. So you need to know that that is not required. Having the name on it is not required. What's required? Well, you've got to have the atomic number. You got to have the symbol, and you got to have the atomic mass. All right, so I want you to label the other two, and you can use A, S, and AM so that you don't have to write all of that out. But pause, label the other two, or at least be able to identify them, and then check back. All right, you unpaused. So this is the atomic number. This is the symbol, and that's the atomic mass. That's the atomic number. That's the symbol. That's the atomic mass. All right, atoms are extremely small. We cannot see them with our eyes or feel them with our hands. So scientists have had to come up with some very small units to measure mass and volume of an atom. So could I use a triple beam balance or a digital scale or a scale like in your bathroom to find the mass of an atom? Exactly. No, it's way too small. It's not sensitive enough to pick that up. What about a yardstick? Could I use a meter stick or a yardstick to help me out? You know what? I'm going to go get one and show you. Anyway, okay. So one of these things, could I use a meter stick or a yardstick to measure the size of an atom? Let's see how wide it is. Of course not. Again, it's way too small. It's not going to do us any good. So scientists came up with this AMU or atomic mass unit. The AMU can be one proton or one neutron. So I also got this because I wanted to show you something. So the radius of an oxygen atom is 60 picometers. So I want to try to help you to wrap your head around what that means. So we look here at our meter stick, and it's got, of course, we know that 1 meter is 1 meter. If we have 10 of these, then we have a decimeter. If we have 100 of these, we have a hectometer. And if we have 1,000 of these, we have a kilometer, right? But then as we take it smaller, we have 1 meter. And then there are 10 decimeters. So that's 1 decimeter, 2, 3. There's 10 of those in here. There's 100 centimeters. And that's what is labeled. That's what the numbers are, is the centimeters. And then the teeny little lines, there are 1,000 millimeters measured here. So 1,000 millimeters, 100 centimeters, 1 meter, all measuring the same length of space. But what I want to draw your attention to is the space in between. So in between my fingernails, that space right there, in between my fingernails, the 1 millimeter space. So come along with me, mental picture in your head, divide that space up into a billion pieces. A billion. This teeny little space, this little millimeter. Think about what that would be like to divide that up into a billion pieces. If you divide that up into a billion even pieces, 60 of those pieces is the width of an oxygen atom. Right? Like, that's really small. And that's one of the reasons why our bodies can use it. We can breathe in that oxygen because it's so tiny, and our bodies can use it because it's these super microscopic little particles. Now, do realize that oxygen, O, just by itself doesn't float around. It bonds together with another oxygen atom to make O2. So when we breathe in oxygen, we are breathing in O2, but that's a whole other ball of wax. All right, so there was this guy named Dmitry Mendeleev. I don't know. I'm not Russian. I've heard it a number of different ways said, but Mendeleev. At 13 years old, this dude figured out the patterns of the periodic table. That makes you wonder what you're doing with your life, right? We only had about, I think, 60. Well, there it is. There were about 60 elements that we knew of at the time, and there was no periodic table. There was no organization to them. And he took some index cards and wrote out the information that we knew about each of the elements, one per card. And then he spread them out on the table, and he just started moving them around. And he realized that there were elements that we hadn't discovered yet. Like, he knew. He was like, okay, this one goes here and this one goes here. Obviously, there's something that goes right here that we just haven't found yet. I mean, it was really brilliant. Smart cookie right there, figuring out the periodic. I mean, he really did. He's the father of the periodic table. Like, he gave it to us. He figured it out. He said, okay, this is where these things go. And nothing has proven him wrong. And in fact, things just keep proving him more and more right, that there are families and that there are things that make all of these elements related to each other. It's really crazy. But I need you to remember the patterns of the periodic table. So there is an acronym to help you remember that, and that's PAVE. Now, the P in PAVE just stands for patterns. So the P isn't supposed to help you remember anything except for the fact that, oh, yeah, this acronym is telling me the patterns of the periodic table. So what are the patterns of the periodic table? Well, the first one is atomic number. All right, well, what's that pattern? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way to 118. It's a boring pattern, but it's a pattern. Counting by ones is a pattern. So your atomic number pattern is by ones. All right, valence electrons. The valence electrons are the outermost electrons, and we'll talk more about them in the next unit because they are what's involved in all the chemical reactions. But those valence electrons definitely have a pattern. Everything here in family 1, 1 valence electron. Everything in family 2, 2 valence electrons. Now, these here, the transition metals here in the middle, they don't play by the rules. You don't have to know those rules until chemistry. So we're just going to skip that group. Let's count and see how many there are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 of them. So we're going to skip 10. So we get over here to family 13. How many did we skip? 10. What's 13 minus 10? 3. Guess how many valence electrons everything in family 13 has? 3. And everything in 14 has 4. 15 has 5. 16 has 6. 17 has 7. 18 has 8. Now, these down here at the bottom actually fit into the transition metals, so you can ignore them too. Both of these groups are transition metals, and they don't play by the rules, and you don't have to know those rules until chemistry, so don't worry about it. But up here at the top, you need to know everything in family 1 has 1 valence electron. Everything in family 2 has 2. Then we skip a few. Then 3, 4, 5, 6, 7, 8. All right, so the pattern is just 1 through 8, and then it goes back down and 1 through 8 again. So the pattern with valence electrons is 1 through 8. All right, energy levels. We're going to talk more about energy levels in notes 1F. So basically what I want you to do for this is just write down what I'm writing down and don't worry about not understanding it right now. Okay, so we have energy level 1 that has a sublevel of S and it holds 2 electrons. Then we have, then there's no other energy levels. There's no other sublevels on energy level 1. Then we go to energy level 2. It has sublevel 2 and sublevel that holds 6. Then we have energy level 3 that has 2 and 6 and 10. And then we have 4 that has 2 and 6 and 10 and 14. And then energy levels 5, 6, and 7 have the same sublevels as energy level 4. Now I know, oh my God, Ms. Harris, what in the world? Don't worry about it. I promise when we get into notes 1F, I'm going to teach you a way that it's easy. For right now, just know that it's complicated and write that down and you'll get it in a minute. Okay, so to review, what are our patterns of the periodic table? What's the P stand for? The patterns of the periodic table are, all right, it's PAVE. So what's the A stand for? Right, atomic number. And the atomic number tells you the number of protons in an atom. All right, what's the V stand for? Valence electrons, which are those outermost electrons, the ones that are farthest from the nucleus, the ones that are involved in the chemical reactions. And the E stands for energy levels. So those energy levels are the different rings that the electrons travel around in. Okay, so what's going on with those valence electrons tells you whether or not an atom is stable, reactive, or somewhere in the middle. So we've got these noble gases over here in family 18. They all have 8 valence electrons, and 8 is the happy, stable number. 8 valence electrons means all my friends are at the party and there's nobody extra here that I don't want here. Happy, stable. I'm not trying to leave. I'm not trying to go get somebody else. I'm happy, stable, noble gases. That's why they're called the noble gases. They're regal and stable. They're noble. So the noble gases have 8 valence electrons and they are very stable because they don't have any room to take anything else in and they don't have anything extra that they want to get rid of. Then you have the families like the halogens and the alkalis that are highly reactive, either because they only need 1 electron to get 8 or because they have only 1 extra electron. And if they get rid of that 1 extra, they'll go back down to 8 and be happy and stable. So that's where the highly reactivity of family 1, the alkalis, and family 17 the halogens. That's why they're like that. Okay. So we're going to talk more about that later too. Don't worry. So let's look at, let's look at if an atom only has one energy level, it's full when it has two valence electrons. So there's only two atoms that are like this, hydrogen and helium. Okay. So hydrogen has one proton. And because of that, that first energy level only holds two electrons. So he needs that second electron. So hydrogen's not stable. That's why hydrogen is in this family here of alkali metals. Hydrogen's not an alkali metal, but it's highly reactive because it only has that one electron. Helium, though, has two protons, and then it has two electrons. So he's happy, he's stable. He doesn't have any empty spots that he's looking for more. He doesn't have an extra one that he needs to grab. He does. He's got an empty spot that he wants to fill in, but he's all set. So that's why helium's a noble gas. All right, if an atom has 2 or 3 energy levels, it's full when it gets to 8 valence electrons. So that's the ones that we're talking about. All of these have 8 valence electrons, have 2 or 3 energy levels. So let's look at argon. No, that's too many. Let's do neon. All right, so and I'm going to compare neon to, let's say, chlorine. So chlorine has 17 protons. So it has, and I'm going to abbreviate here to save time. So we've got 2 electrons in the first energy level, 8 electrons in the third, in the second. Come on, really? By the way, E minus is the symbol for electron because it's negative. And then it has 7 in its outer layer. So that means it has one empty spot right there that it just, it wishes it had an electron there. And that's why chlorine is so unstable. That's why chlorine gas was used as a poison gas in World War I. It is highly reactive and unstable. That's one of the reasons why your mom fusses at you by making sure you put the top back on the bleach. Because if you leave the top off the bleach, the chlorine just goes, escapes into the air, and all you have left is kind of grody water. That's why it's kind of slimy. Well, the slimy is because it's basic, but that's a whole nother lesson. So what about if we have 8 valence electrons out here? What if we're looking at neon? So neon has, I really should do argon since I did chlorine. Oh well. All right, so argon. Argon has 18 protons, and it has 2 electrons in its first energy level, 8 electrons in its second, and 8 in its third. So he's happy, stable, ready to go. Now, if an atom gives away its valence electrons, when it bonds with another atom, it becomes stable. So this is why we can end up with something like sodium that has 11 protons, and therefore it has 1 extra on the outside. So we've got I need to write that twice. We've got our 11 protons, and then we have 2 in the first and 8 in the second. And then there's that 1 extra in the last energy level. And that sodium wants to give it away. So that's what it does. It gives it away to guess who? Chlorine, right? Because chlorine's the one that wanted it. And that's when we end up with a positive sodium atom and a negatively charged chlorine atom. And what do positives and negatives do? Attract. And what do we have there? That's right, salt. That's how salt gets made. When, we'll talk about that later. This video is going on long enough. All right, so I'm fairly certain that's the end of these notes. Yes, it is. Okay, so the next thing is to do the atoms check for understanding. You can retake that over and over until you're happy with your score. Make sure you read the directions if you want it to score it for you correctly. Otherwise, you've got to wait for me to come back and score it. If you spell something wrong or if you don't type it in the exact right way, it's going to mark it wrong even though you're right. You got to wait for me to come back and grade it if you're not going to follow the rules that I set up for grading. Does that make sense? Anyway, have a lovely day. Make good decisions. Bye.